Edmon Begoli, lead of AI Systems R&D at Oak Ridge National Laboratory. Welcome back to the Data Exchange podcast.
Hey, thanks. Great to be here.
So many topics to talk about, but let's talk about, first of all, your upcoming talk at the Data Plus AI Summit in San Francisco on adversarial AI, adversarial machine learning. So before we do that, quick question. How do you pick the topics you work on at Oak Ridge? So what's the remit? What's the mission of your group?
So the mission of our group is to support, first I would say it's very practical. Even though we are a research unit, we really engage in a applied research where different federal partners approach us with problems that they cannot solve themselves. Sometimes these problems are either outside of the expertise of industry, they're sometimes outside of the interest of the industry. So we fill that special role where we either look at the state of the art that came out of industry or academia, or we have to advance our own state of the art because, like I said, some problems. I'm just going to use, we're not necessarily working on that, but let's say look at the problem of a climate change. Okay, so that federal government has interest in reducing certain emissions and so on. And so typically federal government comes to national labs to help with that, to do climate modeling, because just there's no a real big, at this point, commercial, I mean, there is a growing commercial interest in renewable energies and things like that. When it comes specifically to, studying effects of the climate, they typically come to the national labs. So in my case, we support various different federal agencies with applications of, and I use this gently, with applications of AI in federal space, because that's a very broad term, but I can through one question answer probably two questions, and that connects to the topic. Typically what happens, we observe some practical problems that have to be solved. And we started 20 or 15 years ago with really collecting and assembling lots of data that national agencies are collecting and using, and sometimes not connecting and sometimes not using. So we helped them with that. Then we understood that in addition to having the data, there's a great potential to analyze it. So we evolved, in terms of data science, machine learning / AI. And so the topics typically come from very practical problems. And as an organization, we sit between the academia and industry in a way that we like to look at what industry is doing in terms of advancements, but we also like to see what's coming out of academia in terms of state of the art and bring that together to the need of the federal agencies. And so that honestly generates more problems than we can tackle. And so it's easy to come up with the problems. The hard part is to focus on the ones that have the largest impact, and they're also the most interesting for our research organizations to do, because like I said, we applied research, so we try to work on real things, but at the same time, we want to keep our colleagues excited about what they're working on.
So adversarial machine learning, as best I can tell, has two main areas. The first is, it seems like generating adversarial examples somehow, right?
Mm-hmm.
So the people who publish papers on adversarial examples. And then the second area is generating tools and techniques to make machine learning more robust to adversarial attacks.
Yeah.
So how did you end up in adversarial ML?
I'll tell you that in a second, but I'll add a third area, which sometimes gets missed, but we're paying attention to that, and that is using AI to fool humans. So typically when you think about the adversarial AI, we think about the computational methods to fool AI, but we also look into the problem of a deepfakes of very different kind, and generating content, which is not only what we see in typical, regular casual media, like human deepfakes, images, videos of people and, kind of celebrities, but also generating all kinds of confusing content that can pose issues. So I would say that's probably a third area that is not typically bundled in. But as you said, the focus really in a very traditional way is to actually, let me say this first. My talk is going to I'm going to present a taxonomy of adversarial AI. And it covers more than adversarial examples. It covers the whole data supply chain, and that is data poisoning problem. Two is a evasion problems, and that is, inserting adversarial examples to the models during inference times and confusing them. But then there's a whole problem of extraction and inference, and that is extraction, recovering the data, possible private data, sensitive data from
model and data extraction, or model inversion. By the way, before you continue, Edmund, so again, my question: how did you end up in this topic? Mostly, and my interest in this question is mostly because when I read about this field, I get the impression this is cool and interesting, but it's not like cybersecurity where you have headlines every other week of examples, right? So here, Here I struggle to find examples. They seem to be mostly kind of theoretical at this point, right?
That is a great question. And that's the second part of the answer, which I'm going to give in a second, why am I involved in this field, is that I am a researcher, and this is one of those areas of not yet. You don't see headlines yet. There were few headlines, maybe related to deepfakes, when somebody spoofed the call to CEO and have CEO made a money transfer because it was
so that's deepfakes, but then there's huge swath of things around model inversion, model poisoning, things like that. And there's always, great research papers that generate articles, but then when you read the article, it's clearly just an experimental setup and example, right?
So how I got into this, and this will really answer your question. So when I was previously on your podcast, I was talking about our use of, in particular, it was distributed or federated learning, online distributed learning for models in the context of some of the work we were doing in support of the federal agencies focused on healthcare. Some critical domains such as veteran suicide prevention, detection of particular precursors to cancer, making or informing clinical decision-making or life critical decisions using machine learning, and that was all great. And then specifically, that was my narrow area of research, is really natural language processing, and in that context also adversarial natural language processing. And some of the questions there were two questions that we started asking ourselves. One, so the typical process with the modeling is that you take some pre-trained model like BERT, you download the pre-trained BERT, run it on a private data, or in our case was protected data, fine-tune it, and then possibly share it with other entities. And in biomedical domain, it's common to have like a BioBERT or some other things that are fine-tuned variants of BERT that you will share medical community. Of course, in our case, we are working with an exceptionally sensitive data set in terms of privacy. We are working with millions of records of private records, and so we were uncomfortable even about the notion of sharing the model. But that's the right thing to do if you want to advance, biomedical research. If you want to study medicine, you kind of want to share what you learn. And we start asking ourselves questions like, so how easy is to actually recover private data from the model? And this is where we started looking into evidence or our own methods. And by doing literature surveys, we uncovered that there are methods to infer private data from those models. And the second question that we ask ourselves is like, okay, so we're downloading a model that has been trained allegedly on some public data set. What if somebody has tampered with this model? Does such thing even exist, that somebody tampers with the model and then this model does not perform well in a particular setting? To how vulnerable in this model if somebody is feeding clinical notes or images, and one is supposed to make a decision that this person is at risk of suicide or not, or this person is at risk of prostate cancer or not. How vulnerable are these models to manipulation? Having a couple of these questions and doing some background study, this is how we really started with a very well-intended but not necessarily deeply focused question of like, so can we export these models? Can we share them? Can we trust them? And that's what led to this whole, I would say, discovery of the field for us. And also, And I have a paper.
Makes a lot of sense, particularly in the example you cited, because it's in healthcare and in the medical domain. So quick question. You talked about taking a pre-trained model, let's say BERT, and fine-tuning it. So what's your sense of the state of the art for tools for fine-tuning in terms of accessibility? How hard is it to fine-tune a model like BERT? And are there tools that people can use, or did you have to build your own tools for fine-tuning?
The thing is, there's no one answer that answered that question entirely, because it kind of depends on a sub-application of things like BERT. So for instance, in some instances, we have found fine-tuning to be relatively straightforward on some problems that are really understood and widely used. But in some instances, like question answering, and I'll give you a very specific example, of reading comprehension. So there's a subfield of NLP, maybe let's say NLP applications. There is a question answering or neural reading comprehension where one can feed the BERT-based model with a particular text and ask questions from the text. And I was able to show some really remarkable examples. For instance, again, going back to the mental health and suicide prevention, there's a number of, we do this research pretty actively, like interpretation of a opioid safety guidelines. How is one supposed to taper oneself from the opioid therapies or so on? These are 72-page long papers, and it's really hard to interpret them. And so out of the box, BERT-based question answering system was performing really well, and we had some really remarkable examples. But we also found that fine-tuning is not working very well at all. If you need to fine-tune it on some specific domain-specific documents to improve the question answering, our success rate was not very good. And the state of the art, we kind of encountered the bottleneck. So I have a couple of, I also, outside of lab, I also have a academic appointment. So I teach NLP in academia. And so I have students, some very talented people. They're struggling. So I would say that in this area, fine-tuning was not straightforward. In some image analysis areas, colleagues were able to do some fine-tuning.
But Edmon, in many ways, machine learning has become, in many use cases, machine learning has become about fine-tuning, right? Because you start with
absolutely.
You start with a pre-trained model from a model hub somewhere. You're not going to train that from scratch. And
absolutely.
So the question is it usable for my very specific domain or application? And then if it is, then go. If not, then you have to figure out a way to make it fit into your application, right?
Yes, and so I'm gonna have a maybe unpopular answer to that question too. So first, I would say in the ordinary scenarios that I'm not involved in, this has become an industrialized process. One has AutoML and tools in the cloud, and you just follow this process.
And then they even have tools to allow the domain expert to label some extra example.
Correct. Correct. So in that sense, maybe in a corporate setting where you have a relatively mainstream problems, you're analyzing HR data or analyzing some e-commerce transactions and all that, it's probably working fine. In domains that we get to be involved, it's not as straightforward because we typically work on problems that are very specialized. And anything that I've touched in the last 5-6 years, it was a little bit more complicated than that when it comes to, but it absolutely is a mainstream and it should be mainstream. And I think that based on at least what I know in interaction with industry, I think that in that sense, the things have improved dramatically since, let's say, 5 or 6 years ago, when it was first like, am I going to use TensorFlow? I'm going to use PyTorch? Do I need to set it up? How am I going to figure out GPUs and all? It was really involved engineering process where things have dramatically improved. And in that sense,
now I have so many embeddings to choose from.
Oh yeah, the embeddings to choose from and pre-trained models. And I mean, on a positive side, I have a book from Hugging Face guys, and I'm going to be giving tutorial on Sigir on some of the
which by the way, the embeddings are great, but they're also can be confusing to people because there's so many of them, number one. But number two, I think I think it's important for people to realize that you still have to build a pipeline. That's just step one, right? So
Absolutely. And the thing is, and the reason why I mentioned in this case the Hugging Face, I mentioned I think that BERT as a family of BERT models have really I think that's at this point it's a pinnacle of this available pre-trained models that are really helpful. So one can find the one that is efficient, one can find BERT model that is small, one that's very powerful. There's a distal BERT, an Albert, and all those Roberta, and all those variants of BERT. So in that case, I think that this is what I said. I'm offering unpopular opinion that some things are still not there yet because maybe I'm too demanding what to expect from
or maybe your applications just require a certain level of accuracy. Right.
Correct.
So like for example, maybe in healthcare, you can't make as many mistakes as you would in e-commerce, right? So
yeah, right. But in the same time, even in healthcare, I mean, if one wants to strictly work in a biomedical domain, like a vanilla biomedical domain, there's a BioBird, there are things like that are actually quite good. And so overall, I would say that the state of affairs, I think things are getting much better. One thing, if I can complain a little bit, and I wish for a little bit better. So I understand that companies are moving towards API-based access, but I think it was a great thing for the community to have a release of BERT and have a release of these open source models that can be fine-tuned and can be manipulated. And I hope that trend still continues. It's good to put things in the cloud and have access via API, but it's also good for the innovation's sake to have access to a little bit more that you have to open the hood in terms of to work with the models, But anyway, I really praise the whole the Google and the whole.
By the way, there's kind of an interesting trend and counter trend, right? So the mainstream trend is that models are getting bigger, but then the counter trend that I'm starting to see is people are coming up with clever ways to train more efficient, smaller models that are just as useful.
Yes, I mean, fine to predict it.
Yeah, but then I think it's still relative. This is still a relatively new counter trend, but I think it's picking up steam.
It is, and you know what? If I'm to predict the future, this is going to be recorded, and somebody can call me on my foolishness. But if I'm to predict future, I think that this trend of building these mega massive models is going to run out of steam, and I think the computer science innovation and research are going to come up. I mean, there's already work that I track through publications of efficient models that run on CPUs that don't require farms of GPUs. I honestly think that innovation is going to happen there. Innovation is already happening, but I'm seeing it right now in some academic work I've seen out of MIT and a few other. I think that Rice University also had a optimizations to the models where they can run on a single machine or something like that. I don't think that this is going to continue like a Moore's law that every year you're just going to have more and more billions or trillions of parameters. I think we're going to hit the wall there. I think that there's going to be innovation in the architectures themselves.
So here's an area that I think you might actually be already investigating, because I would be surprised if you haven't, but multimodal models.
Yeah, of course. I mean, I will tell you this, that I cannot tell you today myself I'm not going to be able to give you that answer or assessment in great depth, because just in the last 2 years, I've really shifted to go deeply into language processing and specialize there. But colleagues of mine, specifically in work, so in my section, colleague of mine, he's looking into the problem of multimodality, and there's all kinds of interesting things that connect NLP and image analysis and interpretation of the images and interpretation of the multimodal content and kind of sense making.
In the future, if the tools become more accessible and mainstream, this is the way to go, right?
Absolutely, it's a way to go, and plus, it's really a frontier that we need to address, because that's that's the exciting part, is the multimodality of the data, and I think that it's also going to advance the state of AI or true capabilities of AI once we have a robust and effective multimodal interpretation of the content. So all kinds of interesting things.
Here's another area, and it's blowing up, not blowing up, but it's trending quite strongly in academia. There are industry deployments and use cases. The tools are still on the hard to use category. But it's another area that I think of you when I see this area, graph neural networks.
Yeah, so I don't have a great experience with the graph neural networks. I'm kind of getting into it, but I have a colleague that actually works right here across the door, and he is interested in graph neural networks for cyber research, for instance. So that's why he's looking, because you have this complex event space, and it's not necessarily pure multimodality, but you have this variants of different events, and they come at a high speed, and so there's need to correlate and kind of adapt. So he's looking into specifically graph neural networks in that space. So yes, I agree with you, and it's a really an interesting area.
By the way, since you're in a forecasting mood, let's bring it back. Let's bring back something you said earlier about adversarial ML. You uttered the phrase "not yet."
Not yet. So yes, absolutely.
So let me put you on the spot. If not yet, sure. How long before we start seeing headlines routinely?
I mean, first, if I'm to answer this as a human being and a citizen, I would say never, or benignly and mildly. But this problem, and this is why I'm really invested into it, worries me, because I remember late 90s, early 2000, when first serious reports came out around the cyber threat, and some people were not taking it seriously because we were still into like, what's this internet all about? Like, what can we do with it? And then software. I mean, it's kind of hard to. This was 22 or so years ago, but these days it was like client-server architecture, 3-tier architecture, internet, and then suddenly cyber threat. What about the cyber threat? Well, today we recognize cyber threat according to many publications. Civilian and federal and commercial, the cyber threat is #1 threat to the human generated.
Yeah, I mean, for one thing, there's economic incentives, right? So
sure,
and then there's a lot of vulnerabilities. So on the ML side, I guess there has to be enough economic incentives and vulnerabilities.
There are. Absolutely, I can.
So by the way, Edmon, cybersecurity, in my mind, is basically now synonymous with data security, right? Because for cybersecurity, basically they go in there and grab data.
Yeah. I mean, absolutely. To great, I see lots of advanced cybersecurity research. So I know that there are some domains where it's. There's some emerging domains, but I would say the mainstream and beyond mainstream, so a few years in the future, cybersecurity is all about data. To tell you, to go back to the question about
ML,
not yet ML. So we have conducted several experiments, and we are right now in process of recently published one paper, and we are working on some other research that we're hoping to get it published in the fall. Specifically in the area of NLP, but we have also seen some work in cyber, because domains where AI has been effectively deployed is most of the cyber defense tools are AI-based, or at least state-of-the-art. Language processing in general, neural language translation.
But Edmon, in cybersecurity, you have an incentive, right? Because if you succeed, then you grab IP. Data or whatever from the company. In ML, if I succeed, I guess I grab the model. Yeah, is that interesting? What am I getting out of it? If I'm
there's more to. Yeah, there's more to it. So I'm gonna be a little bit, how should I say, coy or reluctant to go too far into vulnerabilities, because I don't want to broadcast them too much. But if you think about it, AI ML or ML, let's say ML, is increasingly a gatekeeper or detector in many scenarios. If you think about it, let's say from a commercial point of view, from a cyber point of view, or if you think about from some other domains, ML is used in either critical decision making, and frequently it has a filtering function. well, what if we can defeat that filter? What if we can circumvent that filter? And most of the attacks, at least in the early phase, and that is data poisoning attacks and
Like
perturbation.
the most common
Okay.
example would be SEO, right? So you can game the search rankings, right? That huge economic benefit, right?
Yeah, absolutely. And then, I mean, there are people with a bad intent. I mean, we can look into the malware and blackmail. So the gain is, of course, in this case.
But in cybersecurity, it's so mainstream that you have ransomware against hospitals in small town America. So ML is not so mainstream yet, right? So.
Well, it's not mainstream yet. The problem is it is so vulnerable that if you are deploying it in domains, so for instance, and I'm not trying to, and I'm really avoiding to even be creative and tell you where the exploitations can exist. That's not my intent. But observed fact, documented fact, is that ML is significantly vulnerable to adversarial exploitation across the spectrum. Number of papers, number of experiments have demonstrated, and we have tested it and tried it ourselves. And like I said, we have a couple of publications in progress where we can circumvent, let's say in the cyber domain or in some other domains of text analysis, we can circumvent and penetrate through ML-based defenses with significant degree of certainty or accuracy, and that's a worrying fact. And I'm purposefully not wanting to talk about.
And that's also, is that, Edmund, somewhat of a function of the fact that models, especially some of the deep learning models, tend to be opaque, and so therefore, you can easily, they're not robust. You can easily perturb an example and make it misbehave.
I would actually characterize that, and now that you're speaking, I probably need to go and modify my slides because these are good questions. And I was, I'm covering I know there are 2 talks for the conference. One is going to be by IBM's R team. They're going to probably talk about a tool, and mine was worth talk about the whole domain and principles and defenses. But to answer your question, it's not even just a black box nature. Black box nature comes secondary, and that is how do we understand how to protect it? But the first problem is what's called the end-to-end learning or representation, end-to-end representation learning.
Exactly.
So that the neural network-based models are really good. I mean, deep neural network-based models are really good and learning on their own based on the reinforcement of their progress towards reducing the error in decision-making. Well, what happens within the neural network through that process is that attention, there's a whole issue of saliency maps. Attention gets formed, or the models get reinforced to recognize particular phenomena in the artifact input. Is it image, is it text, is it whatever? And that presents vulnerability because we can, with the minimum changes to what the model is learned to recognize, we can make it misfire, we can make it misrecognize things. So for instance, if you have
changes at the level that are imperceptible to humans, right? So
imperceptible to humans
for images, but also, actually, I learned recently, Edmund, even for text, because you can take 2 character sets, right? So one, the standard English keyboard, and then the other one maybe Cyrillic, and then you can just kind of insert another character set in there. It still looks like what it would look like in the normal character set, and then
it is. It is unbelievable. And this is really why I'm invested into this. And I'm not saying I'm going to spend the whole rest of my career, but at least I'm going to spend a good number of years looking into this problem because it concerns me. So the research we're right now working on, colleague of mine, Sudarshan Srinivasan and Maria Mahbub and Lindsay Passarella, we are working together on a problem of data poisoning of textual data set and seeing how vulnerable models do. So what we did is we're planning to publish this in ACL for next year. Is we're data poisoning the IMDb data set, and we train the sentiment analysis on IMDb data set, and it has a high degree of the accuracy or F1 score. And then what we do is we take some very small phrases as a data poisoning artifacts, we put them in the data set, and then present it to the classifier, sentiment analysis classifier, and accuracy drops from, again, 90-some% to like 50% or 60% by minimal data poisoning effects. And so what we did is we took the whole BERT architecture and trying to study and to look at like why it happens, how it happens. We don't understand.
But then in practice, this means you have to get a hold, you have to insert yourself in the middle of the training process.
You do need to, but that's not that difficult. So I think that, and my talk is going to be a little bit about that. I think it's more important for the defenders to insert themselves into data supply chain and be able to either verify it, control it, or something. But just
so it becomes like a cybersecurity problem in some ways, right? Because basically,
absolutely.
Yeah.
I look at this problem as an analog to a cybersecurity problem, and that is there are a number of ways, there's a number of vulnerabilities, and there's a number of interventions, and none of the interventions are perfect, and the problem is very challenging. So it really requires a comprehensive approach to addressing the problem itself. And so in my talk, I'll talk about, you know, it's a 45 minutes talk, and I'll probably leave 15 minutes, so it's going to be 30 minutes. So I'm going to just try to.
So now my brain is headed towards kind of more of the industrial examples like Stuxnet, right? So where is ML being used in industrial sector? I don't know, energy, utility grid, or wherever. Insert yourself there somehow. But then if you're, yeah. And then it's more subtle then, right? So you insert yourself in there, they retrain their model, and then you get their grid to do something it wasn't supposed to, right?
So I'm going to avoid those comments, okay, to your question. Yes.
Yeah, I understand your position. Yeah.
Yes, but I will actually give an additional example that I sometimes mention to my colleagues when I tell, or some of the other partners when I talk for the first time. I visit San Francisco relatively frequently. I'm not sure how it looks like now, but when I was driving from the airport up to 101 to the downtown San Francisco, on the left and right there are billboards, and every billboard is advertising AI for cyber. Mm-hmm. And we're the state of the art, and we use AI to defend your networks. You use AI to defend this, and you use AI to defend that. Well, how good is that AI in defending the cyber networks? And so we did some work that is publicly available. The members of my organizations have done some work through what's called AI attack challenges, where they have tested some of these AI tools, and some of these results have been published. All I will say is that I think that industry needs to invest more into making their AI models more robust, because I think that many are rushing towards testing on known data, and then there's this whole problem of unseen data and data that is manipulated, and how the models react to that data. So I'm going to talk about some mitigation strategies at a very high level, because there's a lot that can be said about this. But again, we are rushing into application of AI in some critical domains, and I'm not sure that in these domains or in some of these tools the appropriate steps are taken to protect AI against exploitation. And part of my, I would say, service as a researcher in a national lab is to present this to the broad audiences, to kind of make them aware that this field exists and that they should be looking into mitigating problems as such.
So before we started recording, you had mentioned that you and your colleagues are starting to get back into reinforcement learning in a big way.
Yeah.
So describe some of the use cases and problems that you're trying to use RL for. So
a colleague of mine here at the lab, he's a big adherent. So I was involved to some degree, more or less, as you know, with the RAY project and with Ion Stoika and the team from Berkeley, and I'm still affiliated with these guys. So we looked into reinforcement learning in the past, just out of the sheer interest, but now the couple of us are looking into reinforcement learning as really in some domains like cyber, to develop dynamically adaptive systems that are trained in some of these domains where, let me put it this way, it's very hard to deterministically understand and train models that can respond to, let's say, cyber threats in unknown and emerging domains. And so we're looking into reinforcement learning as one of the ways to, as a path to navigate and train the tools that operate in these complex, multi-factor, large number of parameter spaces. Just like if you think about the gaming and you think about number of decisions that one can take, it's infinite or so large that it's computationally intractable. So when you're looking into spaces like that's what my colleague is really invested into, is the reinforcement learning. We are using it as a how's it called in classical AI, exploration and exploitation.
So you'll need to build
algorithms.
some kind of simulation platform.
Correct.
Right.
Correct. That's exactly what we're involved in. And so it's really, we're pursuing this out of research interest. We have our own, we call it a lab, and the lab in a classical way. This is a research platform where we create our own. We have our own emulators, and we have a simulation of the events, and then we use reinforcement learning as a paradigm in operating in that kind of environment and learning how to respond to seen and unseen events.
And then reinforcement learning at that point could be RLib, RLib.
Absolutely. That's definitely one of the things that we are looking into. And the Ray has a little bit shifted away originally from reinforcement learning, but we are, given that our tools are still Python-based, RLib and Ray as a whole are the.
No, they still. Full disclosure, I'm an advisor to Anyscale. They still have a team of people dedicated to RL and RLib. So it's still a very much a well-maintained library.
Yeah, and like I said, pandemic got us disconnected. So we used to interact with the Ray team and had regular meetings with them. Well, they were UC Berkeley, and I believe when some of them, of course, they shifted to Anyscale, but we had regular meetings, and we're going to go back to it of interacting with the team now that we're back at work. And also what happened with me, the early days of pandemic, we shifted lots of our work towards addressing the COVID-19.
Yeah, I saw your name in some newspaper articles.
Yeah. We did lots of work. It was really good. I mean, it was very intensive, but it was really good. And I mean, that's again function of a national lab, is that when there's some really challenging things that federal government is facing, and they have their own research arm to go to, just like DARPA, they go to national labs and throw things at us, and with the hope that we can help with it. So that kept us busy for early years or early days of pandemic, and now we're going back to just doing general research in machine learning for some specific domains.
By the way, I recently, with a friend, a young venture capitalist, we started looking at the AI and ML space. And, just like many people were, high-level observationists, there's too many companies that are being declared unicorns, right? So there's a unicorn every day. So then we said,
$1 billion,
yeah. So then we said, let's raise the bar. Let's look at companies that have at least 100 million annual revenue. So then that space shrinks. And then it turns out a lot of those companies are focused applications, right? So some in cybersecurity, some in healthcare, and so on and so forth. And then I looked at the skills of the founders, the LinkedIn profiles, you look at their skills. Number one, cloud computing makes sense, right? So, but right up there at the top of that list is distributed computing. Much lower on the list is ML and AI. So then and then it prompted me to do a follow-up post on what's the state of distributed computing for AI. But I think distributed computing is one of these things that we've taken for granted because a lot of the complexity is being hidden from us, but it has become kind of essential, table stakes. Right?
Yeah, I mean, so this is something.
This is our previous podcast episode. You guys were trying to do this kind of large-scale distributed online learning, right?
Yes, and we still are. It's what's happening. So within the ORNL itself, I'm going to first comment on that. So the ORNL is now shifting from runs Summit high-performance computer, which was distributed but collocated system, that was the largest AI system in the world for a while, and then lost its first place and whatever. That's just a typical life cycle of things. And so ORNL is now launching Frontier system, which is the first exascale system. But interestingly, the industry, so there is a development in that space. The team that I represent, for the last year and a half, we have, this just how it comes and goes. We work on the algorithms and try to do the best we can with the algorithms. Then once we perfect the algorithms, then we need to build with the scale. So then you look how to distribute it. So that's how we went. And for our suicide prevention algorithms, we're looking at distributed learning and distributed processing. And then we moved on to strengthen and optimize the, transformer-based networks that we're using in those domains. We're still working on it. Now we're trying to understand their vulnerabilities, how to make them more robust. And honestly, I suspect that especially, so this is, just to call out my colleague, Shanae, who's doing work in reinforcement learning, who's a great researcher. I think that as we start moving towards this renewed focus on reinforcement learning, I suspect that we're going to move next year into how to scale it and how to distribute it. Right now, we are kind of trying to, typically how we operate in this research space is we find important problems, then we try to find the right approaches, or at least a couple of good candidates, and then we start working on those, we start optimizing them, and once we get some good results, typically what happens, we hit the performance wall. We've done algorithmically what we can, now we need to run it on big platforms. So I think that we're going to shift to distributed processing next year, where we're going to do it. And this is what I'm saying, we're going to look into Ray again and try to use it for our own research. But I think, like I said, I'm seeing industry really picking up the interest into high performance and distributed computing, in addition to just running things in cloud, because frequently running things in cloud doesn't mean distributed processing. It means large resource in the cloud that can do something.
Yeah, you should definitely catch up with Ian, because the new lab is Sky Lab.
Oh, I'm caught up. Yeah, I know that there are so yes. I will be their affiliated member as well, and I'm actually excited about the Sky Lab, because it's kind of cool to look into systems again.
I think so. And in closing, you never answered my question about when.
Which one?
When you said not yet, but I wanted you to make a prediction of when these attacks will become common, that we will read about them.
I don't think I want to answer that question. I can because
because Edmond, the reason I'm putting you on the spot is
I know.
I read all these papers and I go, man, this is scary. But then none of the papers really cite any real examples, right? So
well, let's just say that.
Well, I'm not complaining that there are no real examples. It's just that it's an observation that there are no real.
And I'm telling you, we talked about this. There's some answers that I don't want to answer because I do work as a employee as a national lab, and so it's better not to comment on certain subjects.
But you yourself, when you haven't seen articles on commercial companies complaining about this kind of thing, right?
Yeah, so I'm going to comment on something that is straightforward and open for me to comment, and that is when you're talking about academic papers. This is a long subject that I would take too much time to discuss now, but there is one effect. It's great that academic publishing and archive have democratized and simplified the publication process so that people can put stuff out. But I will also tell you this. Lots of that research is not reproducible. I sometimes think that people publish papers to get attention, to maybe get a job at Meta, Google, or unicorn, and say, oh, here's the AI guy because this or person that did this. And we download these papers and we start looking into them and they don't actually work. That's the problem. That is the problem. And so you're probably seeing lots of that. And then this is also a very cool area. Kind of people are excited. Oh, we're going to do some adversarial stuff. So they do little thing and put paper out, and then they just move on to something else. But there is a serious nature to it, and that's why I'm avoiding answering that question, because there is a serious nature to it. But I think that and this is, I'm not pitching my own talk because I'm not representing any special interest, but purpose of my talk on the conference is to inform broader audience, because I suspect that in my audience there might be some people who are working in financial sector, who are working in healthcare sector, who are working in telecommunications and energy, and they kind of want to know about this problem, because it doesn't take that long to turn this problem into.
I just thought, as you were talking, I thought of an area where this might be. There's a lot of economic incentives for this, which is trading and high frequency trading, those kinds of domains, right? So if you can attack an algorithm in any of these domains.
And again, I'm going to be boring and say no comments, but part of the purpose of my talk is I would say as a scientist, is to inform the broader community so they think about the problems like you're thinking, and ask themselves questions. Are there AI-based systems that they're acquiring? Because like I said, cyber, everybody's advertising AI for cyber. There's AI for this, AI for that, for finance. Fundamental question is there AI system? Can they trust it in the face of adversarial exploitation? That is my open question to the audience, and I will present.
By the way, you think about, when there's a data intrusion and theft, the market cap of a company goes down, right? Because it takes a major hit. But imagine if someone attacks an algorithm that's so central to a company's reputation.
Of course.
Make the algorithm biased or something. That could also cause the stock price of the company to decline, right?
Algorithm is involved in a purchasing, hiring, transactions, coordination of other activities and transportation. I mean, we really are moving into adoption of AI across the board. In some instances,
it's just so such a complex problem. Not just, let's set aside the fact that, let's say you're building yourself from scratch the models that you're deploying, right?
Yeah.
So that's already complex. Where's the data come from? The pipelines and so on and so forth, the systems. But in the process of building the models, here's just something, Edmund, that's always scares me, is the Python ecosystem, the dependencies. When you pip install something, you're on your screen flashing all the other things it's installing. You don't know the supply chain of all these libraries.
Of course not. Of course not. Of course not. And that is absolutely so when you had some of these well advertised, I mean, we had a instance with Log4j when everybody had to patch their.
Exactly. Yeah. The equivalent of Log4j in ML, right?
Yeah, absolutely. And stuff like this existed in the Python ecosystem with like SSL vulnerabilities and things like that. So so we've seen that, and you're absolutely right. I mean, that's another significant area of vulnerability when you're just blindly pulling down libraries through pip, through PyPy, downloading code that is, and it's all built on top of each other, which is
on top of each other, right? On top
From a software engineering perspective, this was a holy grail for decades, and that is reuse of the software, now reuse of the components or reuse of the models. That's a really, really good thing. But it comes with these other issues that we really need to take into consideration. So if you remember SolarWinds and exploitation of a software supply chain and all that, I mean, that's something we really need to look into.
Yeah, I mean, if this area becomes a serious area of concern, there's so many attack surfaces where you can find 0 days because there's so many libraries in the ecosystem, right?
So that's why I'm giving this talk. Like I said, I'm not representing. I'm not representing a company. I don't have a commercial interest. My interest is to really speak to broad audiences of experts, or, I mean, my talk is at the, I think, beginner to intermediate level purposefully, because I don't want people to feel like, oh, I need to know deep learning A to Z, even though I'm planning to just pepper a little bit of some introduction. I think the key points I'm going to make is this end-to-end learning representational learning, large parameter space, there are vulnerabilities. But ultimate intent is exactly as through this conversation that you and I are having, as the light bulbs are going in your head and saying, but there's all these areas we did not address. Exactly. I had those light bulbs myself, and I feel it's important to talk about them and talk to people that are concerned about protecting their own systems,
And with that, thank you, Edmon.
Thank you very much. Pleasure as always. Thank you.